Hi there from all over the world. I am Chen Horen, a student from School of Medicine in China Medical University. Today, I'm delighted to discuss the crucial topic of federated learning and its implication for data privacy in collaborative machine learning. Let's begin with an overview of the agenda for today's presentation. We'll first discuss why decentralization can lead to better data safety and privacy, followed by sharing my understanding and experience on machine learning. Last but not least, we'll dive into federated learning, especially its privacy features. To begin with, let's talk about the benefits of decentralization. Decentralization refers to the distribution of control, authority, and decision-making across a network or a system, rather than relying on a central authority or a single point of control. To be clear, here's a graph. This graph shows the difference between the idea of centralization and decentralization. There is no denying that a structure that uses the ideology of centralization, which is depicted on the left, is fragile and can be easily hacked into by just attacking the red dot, which means the centralized server or data storage. In addition, the centralized server reserves strong power by holding too much sensitive data. On the other hand, a structure adopting the idea of decentralization is steady and hard to be broken down. If a node in the system were being hacked, only a small amount of data would be leaked. Besides, none of the nodes in a decentralized system have strong power, since each node contains only a small number of data. And here are some examples for decentralization. Wikipedia should be a prominent example for decentralization, since it allows people from all over the world to edit the article rather than by a group of editors such as that of Encyclopedia Britannica. It is an example for decentralization. Web3 should also be a qualified example for decentralization. Traditional internet uses a system that obtains information from a single source. For instance, when browsing the website of, let's say, Spotify, the browser only connects to the Spotify server. However, with Web3, the information is scattered across the device on the web and thus can be acquired from different sources, reducing the impact of an attack on the server by hacking multiple backups. Another example to this is today's protagonist, which is federated learning, a machine learning method that secures privacy. But before we dive into that, I'm going to share my own experience on machine learning just to introduce the importance of data privacy on machine learning. I usually open data source to train my own machine learning model that can be used to recognize different skin lesions, such as basal cell carcinoma, melanoma, and dermatofibroma, just to name a few. When training the model, I used up all of the pictures given by the source, namely tens of thousands of skin lesion images. If I were to use smaller numbers of photos, the accuracy of the model would be compromised. Although other methods, such as data augmentation, can artificially increase the training database, more image is still preferred in order to have a more generalized result. Thus, more data means better model. However, due to some regulation and in consideration of data privacy, it is dangerous to hold the data in a single place for machine learning. And here is where federated learning came into play. As mentioned above, the privacy concerns with machine learning is a result of that it has to use huge data. Traditional centralized approaches require central servers to access and process data, which poses risks and concerns regarding data privacy. Federated learning aims to address these issues by preserving the privacy of data while enabling collaborative model training. Let's get familiar with federated learning. Federated learning, often referred to as collaborative learning, is a decentralized approach to training machine learning models. It doesn't require an exchange of data from client devices to global servers. Instead, the raw data on the edge devices is used to train the model locally, increasing data privacy. The final model is formed in a shared manner by aggregating the local updates. Here's why federated learning is important. First of them is privacy. In contrast to traditional methods where data is sent to a central server for training, federated learning allows for training to occur locally on the edge device, preventing potential data breaches. The second one is data security. Only the encrypted model updates are shared with the central server, assuring data security. Besides, secure aggregation techniques such as secure aggregation principle allow the decryption of only aggregated results. Access to heterogeneous data is the third one. Federated learning guarantees access to data spread across multiple devices, locations, and organizations. It makes it possible to train models on sensitive data, such as financial or healthcare data, while maintaining security and privacy. And thanks to greater data diversity, models can be made more generalizable. The framework of federated learning itself provides enhanced privacy. A generic baseline model is stored at a central server. The copies of this model are shared with the client's devices, which then train the models based on the local data they generate. Over time, the models on individual devices become personalized and provide a better user experience. In the next stage, the update or model parameters update from the locally trained models are shared with the main model located at the central server using secure aggregation techniques. This model combines and averages different inputs to generate new learnings. Since the data is collected from diverse sources, there is greater scope for the model to become generalizable. Once the central model has been retrained on new parameters, it's shared with the client devices again for the next iteration. With every cycle, the model gathers a varied amount of information and improves further without creating privacy breaches. To protect privacy in federated learning, various techniques have been developed. There are several privacy preserving techniques used in federated learning. This includes secure aggregation and differential privacy. Secure aggregation ensures the confidentiality of model update by employing encryption and secure multi-party computation. And differential privacy introduces noise of or perturbation to the data to protect individual privacy while maintaining aggregated statistics. Let's begin with secure aggregation. Secure model aggregation or secure aggregation. These techniques are employed to combine model updates from local devices while preserving privacy. Methods such as secure multi-party update. Methods such as secure multi-party computation and homomorphic encryption ensure that model updates are aggregated without exposing sensitive information to the central server or other participants. On the other hand, differential privacy protecting privacy by limiting how much a phone can contribute to the parameters of a machine learning model. Therefore, any unique data that can tell a user's private features will be compromised. In addition, differential privacy also adds noise to obscure data. While federated learning provides privacy advantages, It also faces challenges. Let's discuss them briefly. Some challenges in maintaining privacy in federated learning include membership interference attacks. This is attempts to infer information about the presence or absence of a specific data in participants' local dataset. Model inversion attacks. This exploits model updates to reconstruct sensitive information from the aggregate model. Adversarial attacks is malicious participants may try to manipulate the learning process to extract information about other participants' data. Privacy regulations play a crucial role in the context of federated learning. Let's discuss their significance. Privacy regulations, such as the European General Data Protection Regulation (GDPR), provides a framework for protecting personal data. Compliance with these regulations ensures that federated learning systems respect individuals' privacy rights and adhere to established guidelines. Let's explore case studies where privacy-enhanced federated learning has been successfully applied. In a real-world application, privacy-enhanced federated learning was employed to address specific privacy challenges. For example, in healthcare, federated learning allowed collaborative model training without compromising patient privacy, leading to more accurate models and improved healthcare outcomes. The second one is smartphones. Smartphones are one of the most common ways to witness federated learning in action. Functions such as word prediction, face recognition for logging in, or voice recognition while using Siri or Google Assistant or Alexa or whatever a personal assistant are all examples of federated learning-based solution. It helps personalize the user experience while maintaining privacy. The third criteria here is transportation. Self-driving cars use computer vision and machine learning to analyze the surroundings and interpret the learning in real time. In order to continuously adapt to the environment, models need to be learned from diverse datasets to improve precision. Relying on traditional cloud-based approach will slow down the system. Using federated learning can speed up the learning and make the model more robust. In conclusion, privacy is a critical aspect of federated learning, and it plays a vital role in collaborative machine learning. Throughout this presentation, we have discussed the importance of privacy in federated learning and the techniques employed to protect data privacy. Federated learning offers a promising approach to collaborative machine learning while respecting individuals' privacy rights. Thank you all for your attention and engagement during the presentation.